Right, thanks for the introduction. Well, École Normale is my main house. Thank you for the introduction and the organizers for their kind invitation. So since this is a diverse audience, I thought I should include like a very short introduction on magnetic skyrmions before we specialize on whether we could observe a quantum behavior in those systems and whether we can make something out of it. So magnetic skyrmions are these textures like the one you can see here, where they're characterized by topology. So an easy way to see that, we can have like a mapping from real space to the spin space and then count how many times the magnetization wraps the unit sphere. So in this example, we have magnetization going from up to down 1 time, so the topological charge is 1. In a trivial case where we have all the spins point in the same direction as a ferromagnetic state, the topological charge is 0. And at least in the theoretical limits, there is a topological protection, meaning that there is an infinite barrier to go from the ferromagnetic, so from the skyrmion to the ferromagnetic state that is encapsulated in the meaning of topological protection. So after the first experimental observation in 2009, there was a lot of interest in these quasi-particles because they have a lot of interesting properties, including their nanometric size. They're very mobile. The topological stability, as I mentioned, they have a lot of controllable properties, and they allow to build compact and low energy consumption devices. So this is the emerging field of skyrmionics. For the physics that we will discuss today, I'm only interested to know that although these skyrmions appear in these lattice phases, we are interested for isolated skyrmions that they can also be created in a controllable way. As it has been shown by early experiments or on local spin polarized currents or in circular nanodisks, these domain walls can be transferred into isolated skyrmions by the application of a magnetic field. And once we create them, it is also possible to control their dynamics, either by electric currents or magnetic field gradients. That's among the few ways one can manipulate skyrmions. And there is 2 main material categories where these skyrmions can appear. So we need certain interactions that allow this spin swirling in order to be energetically stable. The most famous one is chiral magnets, where we need the so-called Jablonszewski-Morilla interaction to be present. In order for this interaction to appear, we need compounds that lack inversion symmetry. There is a large material category that lack inversion symmetry in the bulk. Otherwise, one can engineer it through thin films on magnetic metals where the lack of inversion symmetry appears at the interface. So if we minimize this model, we can find a very rich phase diagram, including a cone, a helicoid, the skyrmion lattice, and isolated skyrmions. There is a new material category that surfaced a few years ago based on frustration. So here we have ferromagnetic nearest neighbors interactions and antiferromagnetic next nearest interactions that can also produce a very rich phase diagram, including skyrmion lattices and isolated skyrmions at 0 temperature. And in 2019, there is 2 experiments where they observed this behavior in a frustrated compound based on rare earth intermetallics. That's a triangular and a Kagome lattice. The skyrmions that appear here are expected to be much smaller in size, and that will become relevant very soon. So the community thought of various applications. The most conventional one is the skyrmion racetrack, where information is coded on a magnetic material, and skyrmions are moved around to read and write information, or more unconventional ideas, including neuromorphic computing or stochastic computing. This is also becoming a very mature field. So the point here is that we do understand a lot on the skyrmion formation and dynamics and the skyrmion physics. So it's kind of timely to move in a new direction. And as I will claim, maybe studying quantum effects might be relevant and interesting. So skyrmions going quantum, we have a few motivations to do that. The first is the observation of atomic scale skyrmions. So these are very small skyrmions that span a few nanometers in size, like the ones that have been observed in frustrated magnets. And at the same time, we are kind of experiencing like a new era in technologically, because we have the advancement of magnetic sensors that can measure magnetic signals with quantum sensitivity. So it is possible to measure quantum signals in those systems. So this trend follows the general trend of quantum magnetism, not the quantum magnetism strongly correlated systems that would upset Garrett's boss, but quantum magnonics in terms of the quasi-particle picture, mesoscopic physics, as it's encoded in the quantum magnonics field, and a lot of people's work that are present here, that they study the quantum states of magnons and their entanglement to other states, or for example, the existence of topological magnons around Skyrmion lattices that Sebastian has shown in the past. So once we would like to study the quantum effects, there are several things one can try to look for. And based on earlier works of mine, we have shown that quantum fluctuations play an important role on these systems. For example, if we go down to 0 temperature, they are still present and they can change the dynamics of skyrmions. As an example, we showed that it can acquire a mass, or they can be strong enough that they can induce quantum transitions and quantum deepening of a skyrmion that is spined, for example, from a defect. It's also possible to have quantum deepening quantum mechanically. There's another line of research that just mentioned in terms of completeness, where people try to see whether quantum skyrmions can be defined in the true quantum limit of skyrmions in spin 1/2 systems. So just to give you an idea, we have a mesoscopic skyrmion that if it's low enough and at low enough temperatures, it experiences strong quantum fluctuations. And then we can describe its dynamics in terms of collective coordinates. So for example, its position, or some other, the helicity, or some other arbitrary collective coordinate. And then we replace these collective coordinates by operators. And then we can study how those operators can experience quantum effects, and one of them is microscopic quantum tunneling. So this is how we study quantum effects starting from a semi-classical limit. There is an emerging field, and I just mentioned it for reasons of completeness, where we can go in the discrete lattice comprised of spins with a low moment, spin 1/2 or 1, and we cannot replace spin operators with spins, microscopic spins, and there one really needs to solve the quantum mechanical problem and define what could be a skyrmion and what is the analog of the topological charge and so on. But I will focus on this first category, where we have a semi-classical approach in terms of operators that correspond to collective coordinates. Right, so when we have a quantum degree of freedom, that kind of links to something that is really unrelated, which is the field of quantum computing that promises to revolutionize data processing. And there are a lot of activities in very diverse approaches, but all centered around, at the bottom here of the computing stack, around the hardware based on qubits. So these are two-level systems that can behave quantum mechanically. So we are looking for a two-level system that can be two-level microscopically, for example, the photon polarization or the electronic spin, but could be effectively two-level. For example, the superconducting flux in a loop interrupted by a Josephson junction could also have the behavior of two-level system in certain limits. So what I would like to add in this category is the skyrmion helicity. So we have two microscopic states of skyrmions with distinct spin-swirling directions and built a qubit out of that. And since it's not microscopic degree of freedom, we need to make sure it satisfies certain conditions to be able to be a good quantum bit. One is we have unharmonicity in the spectrum, such that we can address only the lowest two-level system, the ability to initialize and control and have single qubit gates. The coherence, it should be relatively long. So coherence should be relatively long, and the ability to scale up the system so that two qubits can be connected. Ultimately, we need to show that a universal set of quantum gates exist, so at least a number of operations we can perform based on this two-level system. So the approach that I followed to construct a qubit based on skyrmions is the following. First, we need to identify a degree of freedom that can be quantum coherently controlled. As I will show very shortly, this is the skyrmion helicity in frustrated magnets. Then we need to check whether a few requirements are met. As I mentioned before, is coherence time, scalability, gates, control, and so on, and whether a few readout techniques exist to be able to measure quantum signals. So this construction has to offer a few advantages. First of all, it will inherit all the appealing properties of classical skyrmions. So due to its size, will allow for compact, high density, and low energy devices. It's based on spin degrees of freedom, so electronic degrees of freedom are not relevant. That means that this, it's going to suffer from different kind of dissipation when compared to charge degrees of freedom. They have microscopic size. That means that it's easily to address them individually, and we can drive our qubit to the quantum regime and tune it by external parameters. And there's a lot of knowledge and technology that has already exists in this field of skyrmionics that is transferable in this platform. But I'll always point out we need to go quantum all the way. So in a way, we cannot expect that the methodology and the compounds we use for spintronic applications are applicable here. So one needs to really put an effort to study quantum effects in these systems. Right, so now kind of want to focus on this degree of freedom of helicity. So here you see various skyrmions. They all belong in the same topological sector, but they have different spin swirling directions. We have two famous categories here, Nell skyrmions on the left and Bloch skyrmions on the right. But any other configuration is also realizable where that would correspond to different helicity. Now, helicity is usually determined by the stabilizing mechanism. So if we have skyrmions stabilized by dipolar interactions, that will give me energetically a term which is cosine of 2 phi naught. Phi naught here is the helicity. If we have the Alonzinski-Morillet interactions, we have either cosine or sine, depending on the type of the Alonzinski-Morillet interaction. So in both of these cases, the skyrmions are relatively large. So for dipolar, they are around 100 nanometers and larger. For DMI, they range between 10 to 100 nanometers. But for this, for geometrical frustration, helicity is a degree of freedom. So any configuration has the same energy. There is no intrinsic potential term. And the resulting skyrmions are also very small. So they range between 2 to 10 nanometers, making it a promising platform to study quantum effects. Right, so now we kind of go back to the quantum problem, and we need to identify our two-level system. So we need to solve a very simple Hamiltonian where we have a kinetic term. Right, okay. So we have a kinetic term where the mass here is proportional to a magnetic anisotropy. If we have a uniform magnetic field, produces a linear term. So a Z here is just the Z component of magnetization. And then we can generate a potential for the helicity, right? If we have a frustrated magnet, there is no potential, but we can generate some terms. The first one is if we have small dipole interactions or if we put strain, we can generate this cosine of 2 phi naught, which gives rise to this double well. So now I think you're seeing where I'm going. We have a double well. Each minima corresponds to different helicities, different configurations. We can apply an electric field that controls the barrier, and then we can apply also a magnetic field gradient that creates a depth difference. Also, if we have a small DMI, will also give the same result. And so the argument here is that these terms could be generated, and it's easily to generate them experimentally with current technology. If we don't have dipole interactions, that gives me this cosine of 2 phi naught. It's possible to do the same thing with strain, uniaxial strain. that generates an in-plane anisotropy and also makes the skyrmions elliptical, and that's something that it has been experimentally observed in iron-germanium thin plates under uniaxial tensile strain. The application of the electric field couples to the polarization of the system, giving rise to a way to tune skyrmion helicity. And magnetic field gradients have also been used now in this context to move around skyrmions in a very controllable way. So going back to the Hamiltonian, it's easy to diagonalize it. We identify the lowest two states. And then we need to see whether a few requirements are met. The first is high enharmonicity. So all the other levels should be well separated. And that's easy to achieve tuning our external parameters. The second is suppressed thermal excitation. So we don't want a temperature that is high enough such that the system thermally excites to higher levels and loses the quantum information. And then once we find the regime where this is satisfied, we can concentrate on the lowest two-level systems and then plot the universal repulsion diagram. So this is the bias. We have away from the degeneracy point, we have two microscopic states, and when we come close to the degeneracy point, then we can have these two states in a superposition. Right, so as you can maybe see, that's very inspired by some similar construction. So it's inspired by the flux qubits. Based here now, instead of the helicity, we have the flux in a superconductor. So in a superconducting loop interrupted by a Josephson junction. And here the two microscopic states correspond to clockwise and anticlockwise supercurrent in the loop. So since there are similarities to superconducting qubits, I mean conceptual similarities because it's still microscopic degrees of freedom, we could maybe construct other types of qubits the same way we have many types of qubits in superconductors. So if we go to a different limit, now instead of having eigenstates of the helicity, we can just see whether we can construct quantum states based on eigenstates of a Z. So this is just typical magnetic states. But we also have a small electric field that gives rise to the necessary nonlinearity. So we can still define qubit states, but now these eigenstates are eigenstates of a Z. And this bears similarities with charged qubits. So there's also one-to-one, where here the Josephson energy, which creates the necessary nonlinearity in the spectrum, is replaced by the electric field that plays the same role. Okay, so since we have identified what are the qubit states, then we have to show that we could manipulate them and we can perform, we can satisfy some requirements. And as I said, there should be a way to manipulate them externally. So we need to see whether we can have single qubit operations where we take a point from the Bloch sphere and we rotate it around a particular axis by some amount of angle. And we also have to show that we can have two qubit unitary operations, which are conditional operations between two qubits. So for the first case of single qubit gates, we can apply microwave fields that couple to the magnetization and consecutively to the helicity. And in the rotating frame, here omega q is the frequency of the qubit, omega is the external frequency, omega capital is the external field amplitude multiplied by an envelope function, and here phi is the external phase. So it's easy to see when we have in-phase pulses, so this phi is 0, then we can generate rotations around the x-axis, or if we have out-of-phase pulses, we can generate rotations around the y-axis. So y and x gates are natively available using microwave fields. So later it was pointed out that if we have a time-dependent electric field now, it's possible to generate the z, so rotations around the z-axis, and that gives us a set of other gates, including the T or the Hadderman gates. So single qubit gates are possible using microwave magnetic fields or electric field protocols. But that's not enough. We need a way to manipulate two qubits. The most easy, straightforward idea is to place them close to each other so they start interacting. That means that the two qubits interact magnetically. But we need to make this coupling to be time dependent in order to be able to produce 2-qubit gates. So it was shown that if we have a protocol where the qubits are further away and then we let them bring them closer and we let them interact and then place them further away, that can generate the CZ, control Z, and control NOT gate. A very similar ideas was explored by G and Jelena and their collaborators using domain wall qubits. So by shuffling the qubits, it's possible to reproduce 2-qubit gates. So the final player is, of course, the coherence. There are two main quantities that we need to study. The first is the longitudinal relaxation that comes from transverse noise and transverse relaxation that comes from longitudinal noise. And a way to at least approach this problem is go back to the way magnetization dissipates. So if we go back to the Landau-Lifshitz equation, there is a phenomenological term. This is proportional to the Gilbert damping that tells us how magnetization dissipates. Now, if we work it out, then that induces friction-like terms for the helicity. And in the qubit language, that gives rise to these random fluctuating noises, but they have correlation functions that are linked to dissipation functions based on the fluctuation dissipation theorem. So starting from the Gilbert equation, we can calculate the relaxation rates pretty straightforward. And all we need to know is the Gilbert damping. So in physical units, we have a qubit that operates in the gigahertz regime. We have high enharmonicity, around 300 or even more. That is easy to achieve. Then we have the coherence times to be estimated in the microsecond regime, where we assume that the qubit operates around 100 millikelvin. Thermal excitations are higher, around 2.5 Kelvin. The main assumption is the Gilbert damping to be ultra low, and a modest estimation for the Skyrmion size, so it's not very small, around 10 lattice sites, and an effective spin to be large, to be 10, relatively large. So this number compares to early experiments on flux qubits, and is at least 2 orders of magnitude larger than the Cooper pair box, and of course could be estimated better by making better assumptions on all these parameters, and also having a better microscopic knowledge of the noise. So this is based on the Gilbert damping only. So finally, we should have a few ways to be able to measure that, and I do theory, and I'm always interested on the feedback from the experimentalists. So magnetic excitations, single magnons, for example, can be measured using hybrid quantum systems. For example, a magnetic system coupled to a cavity mode, coupled to a superconducting qubit, or a spin-active, an optically active spin can be used to measure single magnetic excitations. Skyrmion helicity can be measured using NV magnetometry or CD elastic resonant X-rays. Of course, that's not only enough. These methods need to be combined with some resonance probes. There are some ideas where it's possible to measure resonance signals, microwave signals locally, but it's a bit under, we need to explore it a bit better, what would be the best setup to measure these quantum signals. There is a last point I want to make. I don't know how I'm with time. I'm very close to the end. Okay. So there's a main assumption here that helicity is quantum. So how do we know it's quantum? And the idea goes back to superconducting qubits, where, again, that's a macroscopic system where originally people had no indication can behave quantum mechanically, and first indications came from microscopic quantum tunneling effects and energy level quantization experiments. So in simple words, the phase around the superconducting, around this Josephson junction, at high enough temperatures behaves like a classical object. But as we go down in temperature, there is a critical point where the phase can be replaced by an operator with discrete energy levels and a wave function that can leak under the barrier. And this leak under the barrier signals the tunneling out of it that can be described by a rate that people have measured as a function of temperature. So it's linear in the classical regime and becomes temperature independent below a critical temperature of around, early experiments, I think, 30 millikelvin or so. So these kind of ideas are also applicable for Skyrmion qubit. And we have shown that it's possible to observe microscopic quantum tunneling for the Skyrmion helicity in the millikelvin regime, so around 100 millikelvin. And the amount of time you need to wait for this to happen is only a few seconds, so that's possible. So that's the end of the discussion. The main message here is that Skyrmions can be related to quantum effects. A way to describe that, first of all, is microscopic quantum tunneling, not in terms of helicity that I discussed, but also quantum depinning or quantum nucleation. That's something that also Sebastian has worked in the past. And once we identify the quantum behavior, there are quantum functionalities. There are things that we can build. And the most central idea is the Skyrmion qubits. So thank you for your attention.